My name is John Bent. My pronouns are he, him, and his. I am the Cortex Community Director, and I'm super excited today to talk to you about our big Cortex announcements. Cortex Community announcement, the 100% open source Cortex software, as well as the live drive rack reference architecture powered by Cortex. This is all about fulfilling Seagate's mission to democratize access to mass capacity storage. So in today's talk, I'm going to be explaining our motivation both for creating the Cortex software as well as for open sourcing it. So at Seagate, when we think about data, we think about this study that we commissioned from IDC. What this graph shows is the amount of data year over year that IDC is predicting will be created. You can see there's phenomenal growth in data creation. However, if we look more closely at this data, what we were looking at initially was just the total amount of data being created. And now what we've done is we've separated it into the amount of that data that IDC is predicting will be stored and the amount of that data which IDC is predicting will not be stored. And what we see is that in the bottom, the segment of data at the bottom that's actually predicted to be stored, as an absolute value, it's still growing. There's still tremendous growth in the total amount of data being stored. But as a percentage, as a relative percentage of the total amount of data being created, what we see is that the data being stored is diminishing year over year. Ultimately, in 2025, only 10% of the total world's created data is predicted to be stored. So we look at this at Seagate and we think that there's a tremendous amount of lost potential here. What is happening that larger and larger percentages year over year of the total data created is not being stored? And we ask our customers and they tell us that this is a trend that they're familiar with, that it's a disappointing trend for them, that every single day our customers have to make agonizing decisions about what data can be safely deleted, what data can be discarded. You know, our customers would like to store all of our data, but it's just not economically feasible to do so. So every single day our customers have to make difficult decisions and try and predict which of their data sets will be in the future less valuable such that they can, delete it, even though they would prefer not to. And when we look at this data, Seagate really sees, obviously it's a tremendous opportunity lost for our customers, but it's also a tremendous opportunity lost for the world. What we've seen over and over again is that data science does better with larger data input sets. Machine learning, if you have a larger training data set, produces more accurate inference engines. Data analytics produces more actionable and accurate insights with larger input data sets. So it sounds grandiose, but we can legitimately look at this and imagine if only Seagate could reverse this trend and allow the world to store more and more of this at-risk data, how much of a better place the world would be. If we had better ocean models, how many inches of sea rise could be averted? How many automobile accidents would we not have if our autonomous vehicles were more accurate in their decision making? How many acres of forest wouldn't burn? How many vaccines could we develop? So Seagate looks at this and thinks, what can we do to help our customers? And in doing so, help the world. And so what is going on? Why are increasing percentages of data going untapped? Well, the first thing is that the world needs larger and larger successive individual devices. And Seagate is delivering these. You saw the earlier talks from Ken and Dave all about our HAMR drives, how we've got a vision to produce 50 terabyte individual devices. So I think at the individual hardware level, Seagate is delivering what the world needs. However, the world also needs software to best enable these devices. And Ken talked about it a lot. The hyperscalers are doing a good job. Every single time Seagate releases a new larger disk drive, the hyperscalers are able to immediately adopt it into their data centers. And that's the best economic thing to do because the purchase price of dollars per gigabyte is better with larger devices. And also the operating costs are better with larger devices, with higher capacity devices, because you're consuming fewer data slots in the data center. Now, unfortunately, the hyperscalers aren't delivering those economic advantages onto our customers. Over and over again, our customers have told us that they would prefer to be in private cloud where they have more control, it's more secure, the costs are better. But what we've seen is that private cloud has significant delay when we introduce our large mass capacity devices. The hyperscalers, with their armies of PhDs writing software, are able to immediately incorporate them. The rest of the world needs our help. And so that's exactly what we're doing. We listened to our customers. They said we need to be able to get the software around the mass capacity devices to deliver those devices more immediately into our data centers. And so with our two announcements today of our 100% open source object storage and our 100% open reference architecture live drive rack, that's exactly what we're doing. The hyperscalers have solved this problem, but they're not sharing the answers with the world. Seagate is. We're really excited to announce that today. And today is a continuation of what's been a really long journey for Seagate in object storage, a journey that's been both innovative as well as inclusive. Seagate, since 1999, has been involved in sharing our knowledge about object storage with the world. One of the amazing Seagate researchers, a man named David Anderson, was one of the main authors in 1999 of the original object storage device standard. In 2013, Seagate released our kinetic drives. Those were Ethernet-based drives with an object interface directly in the drive itself. And in 2015, we published that standard working with a consortium across industry in the Connect Open Storage standard. Later that year, in 2015, the European Union selected Seagate to lead SAGE, which was a collaborative vision for publishing research all across Europe, sharing all of these algorithms, mechanisms, architectures to best enable the next scale of computing. Seagate specifically was included and chosen to lead that project due to our ability to deliver advanced object storage. And that's what we're doing today. It's exactly what we're doing today, announcing the 100% open source Cortex and the live drive rack architecture. When we think about Cortex, when Seagate made the decision, we always knew that we wanted to open source it. We always knew that it was about device enablement, about sharing the secrets of mass capacity device enablement with the world. But initially, we weren't sure exactly how we wanted to open source it. And we looked across the open source industry and we saw that what most people do, what most open source companies do when they open source software, they don't open source all of their software. They adopt a model called open core, where some of their software components will be open, but other software components will be proprietary. Typically, they're sort of the peripherals, the user interfaces, some of the things that really make the experience an easy one, right? The ease of use peripherals. So what all those other companies do doing the open core model is they say, hey, come check out our open source software, come join our community. It's really great, isn't it? But if you want the full experience, you have to pay us. And then we'll give you, the full enterprise version of the software. And we thought about that for a long time, and we thought, well, is that what we should do with Cortex? And it doesn't make sense for us. In fact, it's counterproductive to our motivation for us to have some of our software be proprietary. Our goal is to share the software to best enable the world to understand exactly how to use our devices, allow our devices to be, immediately embraced by across the industry, and so that all of our customers can stop having to make these difficult decisions. And so as such, we thought, well, that open core model doesn't make sense. And so we're really excited today to say that because our model is just about sharing the software, Cortex is 100% open source. There's 5 main reasons why we're open sourcing Cortex. So the first is to publish recipes about using that emerging hardware to share the enablement. So I'm the Cortex community director. I'm super excited to have a community around Cortex. I'm also, however, an architect in the Cortex project. And I have to admit that sometimes I like to imagine a world in which every object store out there is Cortex. I'm proud of Cortex. I'm excited for the world to come look at it and see just exactly how cool and innovative it is. But even having said that, I'm aware that there's always going to be a plethora of different data platforms out there. They're all going to have their own, pros and cons, pluses and minuses. And some customers will always prefer other solutions. But what I'm hoping will happen with Cortex, our motivation for open sourcing it, is that customers that still prefer some other solution will go to those vendors and say, I still prefer your solution for, whatever specific set of pros and cons that it has, align very well with my workloads or for the long relationship that I've had with you as a vendor. However, I really like what Cortex is doing with hammer drives. I really like how they've enabled the hammer drives. Can you do the same? And the vendor of that other solution can say, absolutely, I can do the same. They can go right into Cortex, take the open source software, put it into their own system. So we're open sourcing Cortex to publish those recipes. The other is that we accelerate our own time to development. Study after study has shown that open source software is higher quality software. There's also no vendor lock-in. There's no proprietary architecture. We just want to share exactly what it is so that everyone can see. There are going to be some customers that will come to Seagate and say, it's great that Cortex is available as open source, but I would like the supported indemnified version from Seagate, the live drive rack. Those customers can do it, and they'll be more confident because they can, one, inspect the code themselves, and two, because there's no vendor lock-in. They can always move away if they want. And finally, we have happier developers. All of our Cortex developers are really excited to be open sourcing Cortex. They're proud of our software. We're really excited for the world to come see how great it is. And they also believe correctly that when the world participates in the development, that ultimately the product will be even better. The software will be even better. So having said all that, we are announcing today that the software is 100% available for inspection as well as cooperative development at github.com/Seagate/Cortex. We have a Slack channel, we have quick start guides, we have virtual machines you can get up and running and building and testing very easily. We are scheduling a series of Meet an Architect webinars. You can also schedule appointments. You can schedule appointments with myself, with our community manager, with our developer advocate. So please come join us. Again, we're proud of what we've done. We're eager to show it to you. And we believe that with your participation, it'll be even better. So having discussed the open source, our motivation for open sourcing, I want to talk a little bit about some of the architectural design decisions that we made in Cortex that we're really proud of, some of the predictions that we made that have proven to be true. So one, we predicted the need for high performance access to small objects and sub-objects. I think the first generation of object storage was really just about put and get. And typically it was backend. So it was only machines that were accessing object storage as the backend for some other data store that was accessed by humans. What we've seen, however, more recently is that object storage is becoming the primary interface to data as well. We've also seen a lot of artificial intelligence and machine learning workloads that are emerging that weren't there in the first generation of object storage. And what those often do was small random reads. So some of the other object stores out there do not do very well for small random reads. Cortex predicted that. It was designed to do well for those. Similarly, it predicted the need for human-friendly interfaces. Object storage, the first generation, was just machines using it. Now there's more and more humans using it. We really need human-friendly interfaces. Cortex predicted those and designed those, and they're part of the software. We also predicted the need for disk direct architectures. One of the things that we've seen in object storage is a lot of object storage software out there layers on top of local file systems. There's a tremendous amount of overhead in this, both capacity overhead, latency overhead, performance overhead. And it is antithetical to Seagate's primary motivation of enabling the mass capacity devices. So the Cortex software is necessarily directly interfacing at the block interface with the hardware devices so that we can best enable those devices. Also, Cortex has a new architecture for extreme availability to mass capacity, mass density storage. I'm not going to have time in this talk to get into all of these things, but we are releasing white papers, all sorts of materials. So I'm excited to meet with people and share more about the live drive rack and Cortex integration, which also includes a new architecture for extreme durability that we're very proud of. So I want to talk about the mechanisms for data durability that will be available as part of Cortex and live drive rack. As long as the world has had storage devices, the world has stored data on those devices, and it's needed to protect that data from the inevitable failure of the devices themselves. The mechanisms that the world has used to protect the durability of data have evolved over the years, and Cortex and live drive rack is the next instantiation in that evolution. So I want to start with the initial data durability mechanism that was known to the world, and that was replication. That's a very simple method. It works great, but there's a very high capacity overhead for replication. So the world pretty quickly moved to RAID 5. RAID 5 is a mechanism which protects data equally well as replication without as much capacity overhead. You can have anywhere from 5 to 40% capacity overhead with RAID 5. It's configurable. And RAID 5 was good enough for a long time until it wasn't good enough anymore. And the reason why RAID 5 suddenly was no longer a sufficient mechanism for data durability is essentially because disk drives grew larger more quickly than they grew faster. And the time to protect your data from the failures of the devices is bound by the size of the devices divided by the performance of those devices. So the rebuild time was growing, and eventually it grew to be so large that the probability of a subsequent failure during rebuild, which would cause data loss, became essentially deterministic. So RAID 5 was good enough for a long time until it wasn't, so the world introduced RAID 6. Similarly, RAID 6 was good enough for a long time until it wasn't, for these same exact reason. The disks grew larger more quickly than they grew faster. So the world had to invent new data durability mechanisms. The cloud, around that time, moved to three-way replication. So that was like replication, tremendously high capacity overhead, but a safe and easy way to provide data durability. In enterprise, we moved to declustered RAID 6. In fact, that's what runs inside the Seagate enclosures, powered by a set of algorithms referred to as ADAPT. These mechanisms were good enough for a long time, and they're being replaced as well. So in object storage in particular, the world is moving away from three-way replication towards network erasure. That's what you find in Cortex Community. And in enterprise, we're moving away from declustered RAID 6 to declustered erasure, and that's also available in Seagate enclosures. More recently, the network erasure now is starting to embrace something called basic multi-level erasure to get even additional data durability, the necessary data durability that you need for mass capacity storage. The world has moved towards basic multi-level erasure, which is essentially a combination of the declustered erasure in the enclosures as well as the networked erasure. What is unique, however, in the design of live drive rack is something that we refer to as multi-level aware erasure. So the thing that we see, right, with mass capacity storage, rebuild must always be faster. That everything that we just looked at in that previous graphic about the evolution of data durability mechanisms is all about making rebuild faster so that your data durability can be ensured even while the individual devices are growing larger more quickly than they're growing faster. So what we have with the Cortex plus the live drive rack is we essentially are offering innovation from disk to drawer to data. And we're sharing it with the world. Again, Cortex is 100% open source. Live drive rack is an open reference architecture. So what exactly is it? Well, we start with our drives, which we believe, we're very proud to say, they're the best mass capacity storage available. Then we take those drives and we wrap them inside the Seagate enclosures, which gives the best overall dollars per petabyte with the highest capacity. However, the Seagate enclosures, fundamentally what they're doing is they're taking a whole bunch of drives, maybe it's 100 drives in the enclosure, and they're turning those into two giant, very reliable virtual drives, but they're still exposing a drive interface. So then the Cortex software will take multiple of those Seagate enclosures and turn those into the mass capacity storage platform. And there's innovation both in the drawers as well as in the software. So there's innovation from disk to drawer to data. So we're going to talk about that. So looking inside the Seagate enclosure, what you see is you have a whole bunch of physical drives in there. Each one of those drives consists of a whole bunch of platters and individual heads to access the platters. And the drive then exports itself as one two-dimensional array of a logical block address space. It's just a simple array of blocks. And so what happens, however, when one of those drive heads fails? So imagine you have a 16 terabyte drive, and one of those heads fails, as is marked by that red X there. You know, physically, only 1 terabyte has been lost. The other 15 heads are still fine. The other 15 terabytes of data are still accessible. But what's challenging is that those lost bytes from that lost terabyte are scattered throughout the logical block address range. And that's a challenging problem for systems. So what most systems will do is they'll just fail the entire drive. Only 1 terabyte was lost physically, but logically the drive reports itself as entirely lost. So that's, extremely inefficient, but due to the complexity of the software, that's the best solution that the world has had to date. However, inside the Seagate enclosures, we're now solving this. So what our Seagate enclosures do, if a single head fails, it's only 1/16 of the data on one of those drives is lost. And the Seagate enclosure will rebuild that lost data using erasure. It will use virtual spare space to hold the rebuilt terabyte. And it does this in a manner that's completely transparent. So this improves data durability, of course, because the rebuild time is much faster. You're only rebuilding 1 terabyte instead of 16. It also reduces your field repair and replace for, overall improvements in total cost of ownership. So we're really excited about that innovation within the drawer, where we can survive a failure which was previously unsurvivable. And this improves our rebuild rates and it improves our data durability. Well, at the next level, as we get innovation from disk to drawer to data, now what I want to do is I want to think about what does happen inside the drawer when an entire drive fails. So previously we looked at just a partial failure, how the Seagate enclosure improves rebuild for partial failures. Well, it still does happen that entire drives will fail. And when that happens, what we're looking at in these green rectangles is the health of the system. So specifically, this is a system where a Seagate enclosure, a Seagate drawer, has turned 53 physical disks into 1 logical disk. And when one of those 53 physical drives fails, and you're doing an 8+2 erasure encoding, what you'll see is that 19% of your stripes have become degraded because we're doing declustered parity. So what that means is that every single piece of data that comes into the enclosure will be pseudo-randomly spread across 10 different drives. So 10 53rds works out to 19%. When one drive fails, 19% of your stripes become degraded. Now, if a second drive fails, the overlap between the two drives now results in 3.3% of your stripes being critical. What the Seagate enclosures do, which is really very innovative in terms of improving the rebuilds, is the Seagate enclosures are aware of that critical 3.3%, and they will prioritize that rebuild and restore the system to this state. Now, if a third drive should fail, then you'll have 6% critical stripes. That will be prioritized and rebuilt. And finally, then all of the degraded stripes will also be repaired. such that the drawer is returned to full fault tolerance. However, so that's the common case, right? And for the most part, the overwhelming majority of cases, the Seagate drawers are sufficient to provide the data durability that's needed at the system. However, at mass capacity, at mass scale, we know that the uncommon becomes commonplace and pathological failures are possible. So what this slide shows is the system's health after one drive failing, after two drives failing, and then in the pathological case, which can happen sometimes, the third drive fails before the system has been able to complete its prioritized rebuild of the critical stripes. So in this pathological failure scenario, all that's logically been lost is 0.5% of the data. This is totally analogous to the situation that we looked at before in innovation from disk to drawer when one head fails. It's a partial failure loss, but to naive systems, you have to report a complete failure loss. And so that's exactly what happens when other systems run with Seagate enclosures, that in this pathological case, only 0.5% of the data was lost, but the system is not able to deal with that, and it has to lose all of the drives, which in this case was 53 drives. So suddenly the system has lost 53 drives. It's a tremendous amount of data that requires rebuild. You know, traditional file systems say, uh-oh, I hope you have a backup. Traditional object stores, well, they'll frantically attempt to rebuild a petabyte across the network, but that's very challenging. So ultimately with them, it's also probably, whoops, I hope you have a backup. But what we're doing with Cortex and LDR is we're publishing a better solution. And so what we're doing is we're breaking that standard server disk API due to the fact that Seagate is producing both the software and the hardware devices. We have control over their communications. So in this pathological scenario in which only 0.5% of the system was lost, but to naive hosts, the system will have to report itself as being catastrophically entirely lost. What it does in the Cortex situation instead is say, hey, Cortex, I just lost. I had a very small partial failure. Please help me. And Cortex can repair that across the network. So this innovation, which we're sharing with the world, is instead of rebuilding a petabyte across the network, rebuild 5 terabytes across the network. That's a dramatic improvement in rebuild speed for an order of magnitude improvement in data durability. So having said all that, there's a lot more available to educate people about the Cortex architecture. We're really proud of it. We hope that you'll come and join us and help make the system even better. With that, I was supposed to do a question and answer session, and I think I have time for maybe just 1 or 2 questions. So the first one is, how do our developers feel about open source? You know, I mentioned this earlier, they're really excited about it. They're proud of their code. They're excited for it to be open. And they believe that open sourcing software is the altruistic way to make the world a better place. They're really excited about that. Second question is, how will Seagate make money if the software is 100% open source? Well, we're not trying to make money on the software. All we want to do is best enable the world to use our devices. If the world is able to store more data, it's better for the customers, it's better for the world, and it's better for Seagate because we're able to sell more of our devices. So we're excited about the potential of our open source software to share the secrets of mass capacity enablement. With that, I think I'm out of time, but please reach out to me at GitHub. You can schedule a meeting, you can post questions in our issues. Come and ask us questions in our Slack. We're really excited to welcome you into our community. Thank you very much, everybody.